We saw how the forward-backward algorithm can be used to do inference on the z's given a sequence of x's, x1 through xn. But one thing which you can't do with the forward-backward algorithm is find the most probable sequence of z's, the most probable sequence of hidden states for a given sequence of observed states, x1 through xn. And this is what the Viterbi algorithm does. It's called the Viterbi algorithm. It's named after its discoverer, Andrew Viterbi, who published this in 1967. And to illustrate why this is useful, so just a sort of illustration here. I don't know if they use hidden Markov models in this handwriting recognition application, but Viterbi, oh, and it fixed it. Algorithm. That was pretty amazing. Let's see if it works. Hey, there it goes. So, I don't know if they use the HMMs, but just as an illustration to sort of give you the idea of why you might want to get the most probable sequence. In this case, the sequence of characters. You would want to get the most probable sequence of characters, which would be sort of the hidden states. And the observed states would be the sequence of images, sort of, if you could parse those into images, that kind of thing. Okay, so I think you probably know why that's sort of clear. And so we are given here, so the setup, as I've sort of said, is that we're given the x's, x1 through xn, and just like before, we assume the distributions. We assume the emission distributions, x is given z's, and we assume that we know the transition probabilities, we know the transition matrix, and we assume that we know the initial distribution on z1. So we assume that the distributions are known, and our goal in the Viterbi algorithm is to compute the most likely sequence. And let me write that as z star. Z star is the maximizer over all sequences z from z1 to zn of the probability of z given x. So here I'm using z for, z1 to n and x for x1 to n, all the x's. So that's what we're going to do in the Viterbi algorithm. And it turns out to be very similar, actually. I apply very similar ideas to the forward and backward algorithms. So first, let's do a little remark here. I want to make this, just pull out this little observation ahead of time, so we don't have to sort of be distracted by it in the middle of the important part of the computation. So if f is some non-negative function, f of a is, taking arguments a, it's non-negative, and we have another non-negative function with arguments a and b. We'll call it g. So g is the non-negative function on all its arguments. Then we have the following. Then the max over all a and b of the product of f of a and g of a and b equals the max over a on the outside times f of a times the max over b of g of a and b. So in other words, we can sort of pull out the f of a from the inside max here, from this max over b. And this is pretty easy to see, so let me just, to illustrate why this is the case briefly. If you forget about the max over a for a second, then here, f of a is just a constant. It's some non-negative constant. And so, since maximizing over b, g is also non-negative, so f of a is just a constant. It doesn't matter. We can just pull it out of this max, and that's not going to change the result. So that's exactly what happened here. And then we just maximize over a on both sides. So that's just a simple little remark that will be very useful in the following. So next, we are going to compute this argmax, and so let's write that down. Argmax over z. And let's make the following observation. So note that this is proportional to the joint distribution of z on z and x. So this is equal to proportional as a function of z. This is equal to, let me make that a little clearer, the argmax of the joint, because they're proportional. And this is going to be a little easier for us to work with. So let's work with this joint distribution. So let's think about this. So we want to maximize over z, and this is, you know, z from 1 to n. I could write here. So let's think about what's going on here. Let's forget about finding the sequence that maximizes, and let's first just play with the idea of trying to maximize this. Maybe we can find the probability, you know, the number that maximizes this. And then if we can do that, maybe we can recover the sequence in some similar method. Let's see, z and x. So here, if we think about maybe when k equals n, let's think about this. So I wrote down the graphical model for the HMM here, and let's think about, you know, this if in the case here when k equals n, so this is at the end, and then the joint distribution that we're thinking about is it's just the distribution of the whole thing, right? And we want to use the trick for Markov chains, the trick that we always use for Markov chains. And that is we want to find some recursion. We want to find some quantity that we can recurse on. And then, you know, we want to sort of take that thing and find a recursion by using the Markov properties of the model. So here we have this joint distribution here, and we have a max. So let's think about, actually, I'm going to think ahead a little bit here. Let's think about maximizing over z from 1 to k minus 1 here. Think ahead a little bit. So what does that look like? So we had this thing, this joint distribution, and now we're maximizing over these guys. So what we have left is a function of these. So if we want to look for a recursion, maybe we should think about taking n, you know, taking this, you know, k, it would be k, I guess, in this case. I've sort of already drawn it suggestively. Maybe we should generalize rather than just taking k equals n to think about doing the same thing for arbitrary k. So then we would have also this thing maximized over z1 up to zk minus 2, and then this one maxed over z1 to zk minus 3, and so on. So let's think about that. What happens if we try to do that? So that then the quantity that we're sort of recursing on is the max over z from 1 to k minus 1 of the probability of z from 1 to k and x from 1 to k. So I was trying to motivate this a little bit, and I don't know how well I sort of motivated it. But this is the thing. So this is the quantity that we're going to be interested in here. This is this mu k, call it mu for max, I guess. And this is a function of zk. We'll drop the dependence on the x's since we're assuming that they're sort of all known, given to us. So let's think about this max. All right, so let's think about, you know, we're maximizing this quantity, and what is this? How can we use the sort of Markov properties of this thing to get the next one back? So this is the joint distribution over, so we have the joint distribution over these guys, and we want to sort of get a recursion to somehow that involves the joint distribution over these guys. So, well, the natural thing to do would be to pull off, there's a factor for this, we can use the Markov properties, factor for that, and a factor for that. So let's do that. So we can factor this. Let's go ahead and make a new line. We can factor this as the probability of xk given zk. I'm not going to prove, so I'm not going to go and prove all the conditional independence things here. I think you're probably familiar with it enough by now. Probability of probability of xk given zk times the probability of zk given zk minus 1 times the probability of zk minus 1. Well, I guess it's all the ones up to zk minus 1 then. And x from 1 to k minus 1. So you can check that little step. Just, you can use either just the definition of the hidden Markov model that it respects that graph, or you can use d-separation. Either one of those will work. So we have this, and now things are looking good because this here, right? Well, not quite. I mean, it's the joint over z from 1 to k minus 1 and x from 1 to k minus 1. But we'd like to sort of make it look like mu k minus 1 of zk minus 1. So we need to get the max. We need to get a max in here. So we have this little remark now. Let's see if we can use this. So we want to move a max in. We want to move a max over b in. So what we'd like to get would be a max over z from 1 to k minus 2 in here. So let's take that to be b. So let's take our b to be z from 1 to k minus 2. And our a, well, it's the other thing that we're maximizing over, and that's just zk minus 1. So let's use that. So a is on the outside, max over zk minus 1. And then this part here, let's see, is this going to work? Let's check. So this should be a function of a and not b, right, for the f of a part. And this is a, this is b, and that is true, right? Because b is z from 1 to k minus 2. So this will work as our f of a. And this should be a function of a and b, and it is a function of a and b, so that works. So let's do this. Okay, so this is looking good. Probability of xk given zk, probability of zk given zk minus 1. And then, so that's the max over all of that on the outside, and then the max over z from 1 to k minus 2 of the probability of zk from 1 to k minus 1 and x from 1 to k minus 1. Okay, and now things are starting to look pretty good here because we can identify down here. Let's see. So this max looks like this up here. It's just, so here's k minus 1, k minus 2, k minus 1, k minus 1, so it's just one less. So this is mu k minus 1 of z k minus 1. Sorry, I didn't finish writing. This is g of a and b here. Okay, so this is mu k minus 1, and that's good. That's nice. This is known. This is just the emission probability, which we are assuming is known. This is the transition probability, and that's known. So things are looking like we're getting somewhere. Okay, so I'm out of time for this video. Let's stop here for now, and we'll finish up this Viterbi algorithm and see how we can find this max recursively, and then see if we can actually get the maximizing sequence.